To SETI Talks, another production of the outreach of the SETI Institute. We're delighted to be able to bring you a really exciting program today. Again, many of you are familiar with our normal format of an individual speaker giving a deep dive into some aspect of the science we're involved in at the SETI Institute. But today we have a panel of experts who are going to be talking about this recent publication about the planet discovered around Proxima Centauri, one of the closest stars to our own sun at about 4.2 light years away. So this is very, very big news, very exciting news in the science community and for mankind in general. So we're delighted to have a panel of experts to join Gilliam here and talk about this interesting discovery. A lot of you may also be aware of the big announcement that came out yesterday around this signal that was picked up by Russian radio astronomers back in May of 2015 around a star system called HD 164545 and 595, I think. And this is a signal, the nature of which is as yet undetermined, and has given rise to a lot of speculation as to whether or not this is something meaningful. We've turned the Allen telescope array towards that star as of 2 nights ago, and we'll continue to observe and sweep across a variety of frequencies, but that's also created a lot of buzz and excitement in our community over the last 24 hours. So just a couple of other reminders before we get into the talk itself. As you know, many of you know, if you register for these talks on Eventbrite before the talk happens, you'll get a name tag printed out with your name on it and the SETI Institute logo, which will be updated to the new logo, I'm assured, by our crack team shortly, and also the Microsoft logo. And if you keep that badge, that means that for subsequent talks, you just walk right into the lobby, they'll wave you through, and it saves time registering at the desk and signing in. It also saves us, if you keep your badge and reuse it, from having to reprint the badges. So if you are able and you plan to come to multiple talks, please register, hold on to your badges, and make use of them in subsequent talks. And that would be much, much appreciated. Another reminder is that this series of lectures is available on YouTube in our own YouTube library of SETI Talks. So we have now over 360 lectures. I think there's probably a couple of PhDs worth of lecture material on that library. So get acquainted with the library and look at the extensive array of talks on a wide range of subjects in our broad field of science on that series. And lastly, of course, we ask you to keep in mind, we bring this series to you as a public service, and anything that you're willing to do to support us in our efforts to continue these kind of public engagements and this outreach from the Institute, we, of course, are very appreciative of. And you can also go to our website at any time, which is SETI.org, and make a donation, which helps us bring programs like this to all of you. So before introducing our panel moderator, who is our own Dr. Frank Marchese, I wanted to just share with you a quick note from the beloved Andy Fracknoy. Many of you here are familiar with Andy Fracknoy. He's an astronomer lecturer at Foothill College, and he's famous for being the host of the Foothill Astronomy Lecture Series, which is one of the more popular astronomy lecture series here in Silicon Valley. They do about 6 lectures a year during the academic year, typically drawing in crowds of 400 to 600 people. So it's a wonderful series. And Andy is a trustee of the Institute, and I just wanted to share with you a note that he sent me last night regarding this new news about the signal coming from deep space. He said, Bill, thanks so much for forwarding this information to us. I really enjoyed reading Seth's article on the website. That's our senior astronomer, Seth Shostak, who has an article about this on our website. He said, it's a model of clear thinking and a balancing of the excitement of the possible detection with the reality of all the things that might go wrong with a non-verified, one-time wideband signal. Here is where all the important work that Jill, Seth, and John Billingham and others have done in the right protocol for verifying signals. Without the hard work of verification, signals are just noise in the vast spectrum of the universe. We should love it when interesting signals come in, but like a first date, we should not lose our hearts until there's been some verifiable repetition of what happened the first time. So I think that's a brilliant insight. It does raise an important scientific question that I have for Andy, which is, exactly what happened on that first date. Andy. So, all right, without further ado, let me turn the podium over to Frank Marchese. Frank is an astronomer and planetary scientist at the SETI Institute. He's a member of the Gemini Planetary Imaging Team, which is known for its imaging of exoplanets. He's best known for his discovery and characterization of multiple asteroids, his study of volcanism, and imaging of exoplanets. And Frank will introduce Guillaume and the rest of our panelists. Thank you. Frank?
Wow. So I have to have a full room like this to make sure that my CEO introduces me. I love it. Okay, so we're going to start very quickly. I have no idea, Lee, what means this sign, so... Okay. Oh, there is a sign-up that's going to be circulated around. So if you want to be included in our mailing list, please fill it up. And you will receive some spam from us every week about our science series lectures. Okay, so let's move on because we're already 10 minutes late. Well, it's great to see that many people here today in this room. I think last week the view of astronomy has been changing quite a lot with this discovery, and I'm glad that the public, you and scientists, you have been kind of involved in this discovery and have been participating to the conversation. So without having too long speech, I'm just going to introduce Guillaume Anglada-Escude. Guillaume got his PhD thesis in 2007. He has been working at ESA, the European Space Agency, where he developed software and data analysis techniques for the Gaia Space Astrometry mission. After his PhD, he moved to the Carnegie Institute for Science at Washington, D.C., and that's when he started working with exoplanet pioneers like Alan Boss and Paul Butler. He mentioned to me that in a cloudy 2 weeks observing run in Chile in 2001, he get this aha moment that we have all scientists. He realized that the existing data analysis methods did not exploit the potential of the existing spectrograph. And he started developing a suite of new algorithms and codes, which led to unprecedented Doppler precision detections of planets. He then moved to the University of Göttingen in Germany as a postdoc, and he started working on the design and construction of new spectrograph for exoplanet detection around red dwarf stars. So he's an instrumentalist as well as a data processor. So that's an interesting partnership here. Soon after that, he joined forces with Mikko Tuomoi, an applied mathematician who at the time was developing Bayesian and global optimization methods for detection of small signal in time series. So this maverick team, as they call themselves, or people call them, discover new small planets in existing data sets, including most of the potentially habitable ones reported to date near the Sun. The sensitivity and reliability of their methods were finally acknowledged after winning the double-blind test competition organized by the exoplanet community in Yale 2015. In September 2015, Guillaume Anglada-Escude was appointed lecturer, which is equivalent to assistant professor, in astrophysics at Queen Mary University of London. So please join me in welcoming virtually Guillaume Anglada-Escude. The floor is yours.
Okay, many thanks to Frank. And if you don't hear me, just send me a message or something, because I don't see you at all. So only feedback I can get is from text. Anyway, so I'm going to tell you a bit today about why we are reporting this result now, and for example, hasn't happened before, and try to put things a bit in context with what we know about exoplanets and why we are here, in a sense. As you will see, we had the technical ability to detect this planet for the last probably 10 years, and it hasn't happened for a number of reasons. And I'll try to drive you through the process of how this planet was detected or how motivated the following up campaigns and things like this. And hopefully you will get a better understanding why things happen. You have seen it suddenly from 1 week to the next. For us, it's been a long process of almost 4 years since we did the early detection. And I'll try to guide you through this process. So if we get the next slide. So the science doesn't need much introduction, just wanted to have it here for reference. What we are trying to do is to find planets, especially small ones, around the nearest stars, because they offer a number of follow-up opportunities. Especially I'm focused on M-dwarfs. M-dwarfs are just stars like the Sun, but they are much smaller. Basically, they started with less mass, and for this reason, they have less volume, and they also are way fainter. So that produces actually a double advantage in detecting planets that may be potentially like Earth. So the first reason is because the star is smaller, we see the effect of the planet around the star much stronger. So it's proportionally directly to the mass of the star. Proxima Centauri is about 10% the mass of the Sun, so any signal of a planet that's indirectly doing something on the star will be 10 times larger. The other reason that they are useful, and sometimes is not acknowledged, that we have these very faint stars, and then the planets that are warm enough to keep water on their surface have to be very close to the star. What that means is that the orbital periods that we are sampling are very short, which means also that within 1-2 months, under a year, we can observe many times the orbital signal of the planet. So we are using, in this case, for Proxima, we are not using the transit method that has been used for Kepler. What we are using is a classic Doppler technique. It's the first method that was developed to detect exoplanets, which basically measures how the star moves back and forth, because there's a planet around it, and we see the motion of the star along the line of sight. So that's basically it. Of course, when you detect this planet, because the star is smaller, then you can see more things. For example, if there is transits, you can hope to see actually features from the atmosphere when the planet is transiting in front of the star. And eventually, because this is a special star, Proxima is the nearest star to the Sun, we have this hope that eventually we might be able to send some probes to this, maybe in a few decades, maybe in 1 century, but certainly if we don't collapse as civilization, is something that's bound to happen eventually. Okay, next slide. Okay, so these are a few numbers that I already said. So Proxima Centauri, to just put you in situation, it's 12% the mass of the Sun. The radius is comparable also. Luminosity is about 1,000 times fainter than the Sun. The distance, you know, it's 1.2 parsecs, which is 4.2 light years. And for example, there's an important feature that the rotation period is a slow rotating star. It's 83 days. And that will be important for the detection that we'll be showing you in a second. The habitable zone of this planet, where you can put a planet and the temperature at the surface would be warm enough, is about 5% of the distance between the Earth and the Sun, so what we call astronomical unit. And the orbital periods are between 8 and 30 days. So this is where we expect to see these small planets orbiting it, and that are the most interesting ones. Okay, next slide. Okay, so before we did our survey, basically there were tons of observations of Proxima. This is the kind of the conclusion of 16 years of follow-up. The problem with this, when you are looking for a periodic signal, the problem is that you don't know what's the period you want to detect. So you have to sample a lot of timescales first to figure out where is the interesting variability. And here is what the previous surveys had done. So there's the UV survey, the HARPS GTO. We also had our own program trying to figure out planets at very short periods. And you can see that before what we have now today, we had already 500 observations taken on Proxima. And the recent campaign that lasted for 2 months only took 50 observations, roughly. And you might wonder why these 50 observations can overrule 16 years of observations and these 500 measurements. And the reason is, I'll tell you in a second, if we see the next slide. So what happens when we took in 2012 the old UVS data and the HARPS data that hadn't been combined, these were 2 surveys that look at the star with similar precision, we could see that there were 4 putative signals. The one on the left on this diagram is what we ended up confirming as a signal, so it's at 11.2 days. But then there were all these other ones that we didn't know what they were. So any of these could be a planet, any of these could be some artifact from the stellar activity, and that's the thing that we didn't know. Basically, we had this signal, it was statistically significant, but because of this sampling, the star is active, is varying in things in ways that emulate the presence of planets. We couldn't tell if one of these signals or any of them were actually real. So this is when we started to observe the star with higher cadence every day for a couple of weeks, for a couple observing runs, but still that didn't work, and you will see in the next slide why. Here, one back, please. Here, you see in this diagram, the red dots are the measurements of Proxima, and you see when you have a planet orbiting the star, what you would see in the velocity of the star is that it follows a sinusoid. So you see the red dots kind of follow a sinusoid, but our observing run was 12 days long, so we couldn't see this thing repeating. We saw that there was a probable, the plot on the bottom is what we call a periodogram. There's this big, massive thing that telling you, oh, there is possibly a signal there, but then you cannot confirm that it is truly periodic. So these observing runs that were only 10 days long were not sufficient to confirm the signal. So then it was clear that what we had to do is what we did in the pale red dot campaign. And next slide, please. Well, okay, the pale red dot campaign, we had to convince the observing committees. We had to insist for almost 2 years to finally get the data. And when we got it, the campaign was approved. Next slide, please. This is the program that we executed, and that's a list of collaborators, more or less with their technical expertise separated. So here, what we got is the HARPS spectrograph, which is the most precise Doppler machine that we have, especially in the southern hemisphere. And basically, we wanted to observe the star for 60 nights in a row. So we had this signal repeating every 11 days. With 60 nights, you basically sample it 5 times. So we can be sure that the signal is actually repeating, has a well-defined period, and it matches the old data. But simultaneous to this, we also followed the star with a number of small observatories in the south to monitor its activity. We want to see the star flaring, we want to see the rotation of the star, and we want to see if there is anything in the variability of the star in the time scale that we see the Doppler signal. So that's why we used 3 observatories, and in the bottom you will see the list of all the institutions involved. And that's also the reason why we have so many people working on several expertises. We really needed a big team to try to nail it down. Next slide, please. Okay, so that's what we wanted to do. I already told you. Here is the result of the campaign in terms of success of nights. So you see the red spots are nights that didn't work because of weather or other things. So we were very lucky. Apparently, after our run, there was El Nino, so for 3 months they couldn't observe anything at all. But in our case, the statistics were favorable, so we got almost 90% of what we wanted to get. So let's go to the next slide. So this was the situation a bit when we started looking in January this year. So you see this plot again, I showed it before. This is what we call a periodogram. And I'm not going to go into the details, but basically, if you have a signal that exceeds some threshold, these thresholds are these horizontal lines. If you have a very significant one, you would have a very strong peak, single peak, that tells you that there's a planet in that period. So that was the situation in January with the HARPS and UVS data from the previous surveys. Now, we got our observations, and that's what we see in the next slide. So it's the same periodogram, but now only using the new data. So we see the same signal, the same period, and there's one missing step here. We have verified that the period is the same, but now we have to see if these 2 signals are actually the same. And when we combine the historical data with the previous one, this is what we get in the next slide. So you have this huge signal now that is beyond any doubt. Statistically, the probability of a false positive is 1 in 10 million. So we are pretty sure the signal has been there. It's been there for 16 years in a row. And the only thing that now we needed to verify is that there was nothing in the activity of the star that could mimic something as strong as this signal. So in the next slide, you see here in the top, the radial velocity measurements of the star. So this is in the blue line is kind of what you expect to be the signal of the planet. The red dots are the measurements that we get in the recent campaign, and even by eye, you can see the thing going up and down at exactly 11.2 days. And what you see in the bottom is that this is the photometry, the measurements of the brightness of the star. You see these flares happening, marked in blue, and this photometry is telling us that the star is rotating at the period that we expected, 80 days, but there is nothing in the time series that emulates or it's in the comparable time scale of our Doppler signal. And this is where we move from a Doppler signal We rule out that activity is causing that Doppler signal, and in the next slide you will see we go from a signal to a planet. And basically, we know the amplitude of this motion. A larger planet would move the star more. A smaller planet will cause this very small motion, which is walking speed, basically. The orbital period is 11.2 days, basically confirmed by the recent run. And then you just use basic physics, Kepler's law, thermodynamical equilibrium, and you get these basic properties of the planet. So the minimum mass, we only measure the motion of the star along the line of sight, so we don't know the inclination of the orbit. So we are measuring what we call minimum mass. It's 1.3 Earth masses. However, there are reasons, statistical reasons, using Kepler results, for example, or Doppler surveys, that tells us that these planets around this kind of stars tend to be very small. So we suspect that the mass of the planet is close to this 1.3, might be 2, but probably not 4 Earth masses. And then the other thing that you can compute is the final element is take the luminosity of the star and the distance between the planet and the star, and you can guess that the equilibrium temperature, if you put a bare rock at that distance from the star, the planet would be at 240 Kelvin, which is minus 30 Celsius. You might think this is very cold, but actually, if you put Earth under the same conditions, it would be at minus 15 Celsius, and what it keeps warm is having an atmosphere. Okay, so that's what we know, and these are the facts, and I don't want to oversell whatever speculative conclusions can be derived from this. So this is what we have, and we have a lot of panelists in the table that can then give you a bit more interpretation of this result. So that's basically it. I hope you agree with us that the detection is spectacular in a sense, statistically, a lot of technical details here, but we are very happy that we finally spotted a planet that's potentially like our own around the nearest star.
Okay, so we're going to enter in the second part of this colloquial series. So I'm going to ask our panelists to come here. We're going to have a discussion on this discovery with Guillaume. The first panelist, I just would like to say that, I decided to invite la crème de la crème of the exoplanet detection in the Silicon Valley. So we have here a great team of researchers who works in different institutions. So first we have Natalie Battaglia. She's an astrophysicist at NASA Ames Research Center and the project scientist of the NASA Kepler mission. She holds doctoral degrees in astrophysics at UC Santa Cruz. She has been involved in the Kepler mission since the proposal stage and has contributed to many aspects of the science. She's co-author of NASA 30 Years Roadmap, which has a chapter devoted to the search for life. And she serves as well at numerous NASA Science Advisory Councils, such as JWST and LUVOIR. On your right here, we have Tom Barclay, who received his PhD from the University College London in 2011, who has worked on ultra-compact white dwarf binary stars, and is currently the director of the Kepler K2 Mission Guest Observer Office at NASA Ames Research Center. Tom works with astronomical community to utilize Kepler data, which has led to hundreds of astrophysical and planetary science discovery. On the right here, we have Chris Burke, who received his PhD in 2005 at the Ohio State University. Chris has led numerous discoveries of exoplanets, and I kind of was laughing when I read your resume. So I'm going to just say that he discovered interesting planets such as XO2b, XO5b, two Earth's Jupiter's transit exoplanet, and Super Earth GJ1214b. Everybody knows those, right? GJ1214b is the first well-characterized subneptunian extrasolar planet orbiting around the M dwarf. So he's going to talk to us about bringing his expertise on planet distribution as well as the search for exoplanets around M-type stars. And finally, we have Eduardo Bendek, all the way here on the right, who has a PhD in optical science at the University of Arizona. His dissertation's result, this is also very cool, was about the first demonstration of a multi-laser ground layers adaptive optic system. Since 2012, Eduardo is working at NASA Ames to develop technologies for exoplanet direct imaging and characterization. And I think he's going to talk to us today about the ASCESAT mission, which is dedicated to directly image planets in habitable zone of Alpha Centauri A and B. And I'm going to start here with maybe a conversation, a discussion between Nathalie and Guillaume. Guillaume, you gave a very good talk where you showed basically the results, the number in a very neutral way, so the data that we have. So I would like Nathalie maybe to comment a little bit about the discovery itself, and maybe tell us what if she thinks we have discovered here an Earth-like exoplanet, and if not, why not, and what is missing.
Okay. Well, first of all, Guillaume, congratulations to your team. I've already had one talk with you, but I didn't get a chance to say that. So Frank asked me to maybe say a little bit about what my first reactions were to the discovery. So like any good scientist, my first reaction was skepticism, right? And like any good scientist, my second reaction was intense wonder and excitement. So can I just say a couple things about those? So first, the skepticism, right? We've been spoofed before with alpha cen b, little b. So you want to see the signal, you want to see the data, you want to understand what due diligence has been carried out to guard against other kinds of false alarms. And I think he did a great job of showing that they did do that due diligence. So I was convinced about the signal strength, but then I asked myself the question, well, geez, what are the chances that we found a small, potentially habitable planet orbiting the nearest star? I mean, come on. And actually, that's something that we can weigh in on, that Kepler can weigh in on, and I'm sure Chris will say more about that. But basically, what Kepler has taught us is that the nearest potentially habitable Earth-sized planet is expected to be within 10 light years of the solar system, orbiting an M dwarf, which is this host star. And so then I asked myself, well, how many stars are there within 10 light years? And the answer to that question is only about 7. So yes, we are lucky, but we're kind of roll of the dice lucky. We're not winning the lottery lucky. Had it been the latter, I probably would have been a little more skeptical. But rolling the dice, I'm good with that. With regards to wonder, as a young student / postdoc, I spent time moving back and forth between Brazil and the US. And in Brazil, I lived on the side of a mountaintop overlooking the ocean, and perched above the ocean was Alpha and Beta Centauri. It was like the last thing I saw every night when I went to bed, right before going to bed. And yet, as a stellar astrophysicist, I never actually looked at those and wondered if there were planets there. It just wasn't in my consciousness. But also around that same time, Michel Mayor announced the discovery of the first planet orbiting a normal star, right? And I had no idea how much that was going to change the course of my career. And now fast forward just 20 years later, we've got 4,000 exoplanets. We know that every star has at least one planet. And we know that the nearest potentially habitable planet is really close. And so I just offer that because I think it's going to be amazing what the next 20 years brings. I think if Archive over the last week is any indication, there have been 10 papers posted just since this discovery last week. We're going to see a tremendous amount of progress over the next 20 years, and I'm really excited to see what that brings. So is this really an Earth-like exoplanet? Ever since Kepler launched, this word Earth-like has been a loaded phrase. It can mean many different things, right? I mean, we measure something about the size or mass, we measure the orbital period, that's all we know right now. So it's a bit of a stretch to say that it's Earth-like. What we know is that we have a small planet in the habitable zone of an M-type star. That's what we know. Could there be life? Yes, absolutely. But is it Earth-like? It's not orbiting a star like our sun. It's orbiting an M dwarf. It's orbiting at a very short orbital period. It's receiving a lot of X-ray and UV radiation. It could be tidally locked, et cetera, et cetera. So there are many ways we already know that this system is very different. But that doesn't mean that it's not inhabited or habitable.
Yeah, I would like to stress this that Natalie just said. Thank you, Natalie. Stressing that this is a whole new world. It's actually not fair to call it Earth-like. It's a completely alien place. As you said, with high chances this is tidally locked, and there can be amazing discoveries or even things that we cannot imagine that are happening in this planet. So I think that's actually more exciting than thinking that this is an Earth-like planet in the sense.
So, Tom, I know you have been interested in life on around M-type stars, because you have discovered some interesting, your team discovered some interesting candidates and with Kepler. I think you published a paper about something related to how life will be, and what kind of different environment we have around M-type stars. Can you elaborate a little bit about this?
So M dwarfs are extremely different environments from our own sun. M dwarfs are much cooler and much smaller than our own sun. This makes them very different and unusual places to look. I think a number of years ago, people weren't thinking about looking for life around M dwarfs. And now it's become very exciting and really at the forefront of where we should look. And there's a few reasons for this. For me, what excites me is that 70% of stars in our galaxy are M dwarfs. If we want to find life and find if life is common, if it exists around M dwarfs, then it's common in our galaxy. It's everywhere because most stars are M dwarfs. Most stars in our backyard, or stellar backyard, or cosmic backyard, are M dwarfs. They're everywhere. And also, so that's one reason. They're a great place to look because they're common. The second reason is they're the easiest places to look. It's not coincidence that we're finding planets around M dwarfs. We're finding the most exciting, perhaps, planets around M dwarfs. It's simply because it's the easiest place to look. That's for a few reasons. From Kepler and from ground-based transit surveys, the transits appear deeper, the signals are easier to detect. Also, from radial velocity studies like this, the amplitudes are greater than they would be for a planet orbiting around a sun-like star. Secondly, the habitable zones are closer in. The cooler the campfire, the closer you need to be to the fire to keep warm. And that's exactly what's happening here for the exoplanets. They're close in, you see more signals, you see them repeat frequently. Guillem's team was able to look at this star over the course of a season or a couple of seasons, a year or two. If it was orbiting a sun-like star, he'd need to spend decades of work, and this simply wouldn't be feasible to do with our technology as of today. So there are some reasons for why we're finding this. But life would be, if there's life on these, it would be very different. Natalie touched upon this. These stars are a pretty extreme environment in terms of the radiation they receive. This star has flares every 20 minutes. It has a flare, a small flare, but a significant flare. It has about 66 flares a day. Often it has more than one significant flare going at a single time. It averages at about 8 super flares a year. So this is pretty extreme. In fact, the X-ray radiation coming from this star is about the same as the X-ray radiation coming from our sun, but you push this planet really close, and you're getting a really significant whack of X-rays all the time. So this becomes a challenging place to think about how life is. Our problem is, and this is a problem I hope is going to be solved soon, is when we think about life, we extrapolate from a sample size of 1. And in science, extrapolating from 1 is not usually a way to get good data and good results. So just because life on Earth wouldn't evolve on these planets doesn't mean life couldn't. But it would certainly be alien to us.
Okay, Guillaume, I think you can hear me. So the two panelists here, the first one, they both mentioned that in fact, to find exoplanet or an M-type star is kind of a shortcut to find life, maybe in our galaxy. So now I'm going to have a very practical question: is why then it was so difficult for you to get telescope times to finalize this study? You mentioned that in your talk, and I heard about it as well. You have to wait 2 years for that. So what was the skepticism here?
This is not. I cannot answer this question. You can ask to the telescope allocation committees. No. I have a very strong opinion about that. I think it was pretty exciting. I agree that the initial signal was tentative at most, but then we started to accumulate data, and I think the case was getting really, really strong. I think one of the skepticism that was here is why the HARPS team, for example, that has been observing the star for many years, and why the UVES team didn't report the signal before, with so many data already accumulated. But this is something that we learned recently, or kind of makes sense that these stars have this variability from age and other things, and you really need to sample the orbital period a few times consecutively to be sure that what you see is coming from the star. Otherwise, basically you see the star here, and then 2 months later you see the same signal, but they are shifted because the star changed its state for some reason, and there's no way to match the data of different seasons. Now we have this signal repeating 6 times, and now we are sure, we just see it by eye. The statistics are only telling us what we see very obviously. So this paradigm shift of doing these dedicated experiments is something that I think people really need to think about this, because this is about exploration. These are the nearest stars. It's not about a population analysis. This is what Kepler and the space missions can do very well. And this is basically exploration of our neighborhood. And this needs dedicated experiments, basically star by star. This is a bit of one of the lessons learned here as well.
Okay, so I'm gonna bring us to the transition with Chris. I wrote a blog post about the discovery last week, shortly after the announcement. And I was mentioning that what we are doing as an astronomer right now, we are exploring the nearby environment of Earth. We know now, we have mapped basically the stars. But now what we're doing is like the explorer in the 18th century. We are mapping now the planets and around those stars. And we're trying to characterize those planets, building a 3D map of the closed environment of the sun. So your work has been a lot about quantifying the number of exoplanets around different types of stars. And can you give us an idea of how many exoplanets we will see around Earth, considering the closed environment of our sun, and how did you do that?
Yeah, certainly. We've had a big phase shift, I think, is a good phrase, in our thinking of extrasolar planets over the last 10 years. When I got started, in graduate school, which was around 2000, we just had our first extrasolar planet discoveries. They were large planets, Jupiters. And that really got me really started down this track of what else is out there. We find these Jupiters. We were shocked to find these Jupiters on periods of 3 days, 10 days, sitting right next to their stars. So that really jump-started, I think, a lot of people's thinking of, asking these questions, are we alone? And so throughout my career, I've been following this path of finding planets of smaller sizes at longer orbital periods. And then finally, I had the opportunity to work on the Kepler mission, which was just a total data set that we've never had before, and really unprecedented sensitivity to planets. And so when I started my career, we didn't know what was out there. And with Kepler, we had our first glimpses of planets like the size of Earth, measuring their radii, also radial velocity surveys with the HARPS telescope was also finding planets of very low mass around stars like our sun. So we've seen this progression. I think the discovery of Proxima b really is kind of a putting down a marker, a new marker in this discovery. From Kepler, we were surveying planets, stars very far away. Kepler was a mission staring at the same set of stars around sort of like an area of the moon for around 4 years. The Kepler mission lasted and didn't move. It looked at those same stars for 4 years without interruption. And with that sensitivity of the telescope we have with Kepler, we were able to find many, many extrasolar planets, planets like we don't even have in our own solar system. So things like 2.5 to 3 Earth radii are very common for stars outside of our solar system. So on this journey, we've really just found from Kepler is that these kind of planets are very common. The numbers that we like to throw out nowadays based on the Kepler data is that if you include all periods and planets of all various sizes from Earth size up to a Jupiter, basically what we're finding is on average 1 planet to maybe more planet per star is pretty typical. So what this means is if you go out and observe, if you were able to actually go visit 100 stars and survey in person these planets, some planetary systems you would find nothing, they would be barren. Some of them you would find a huge number of planets, 5, 6, 7 planetary systems, sort of like if you were to come here and see 9. So on average, though, from our detectability from Kepler, on average, when you visit 100 stars, you're going to find at least 100 planets, probably more, of various sizes and orbital periods. And so this result has only come out in the last 5 years from Kepler that we've been really finding this. And it's truly remarkable, especially what we find from Kepler's M dwarfs look very different. They have a much higher probability of hosting planets than stars like our sun, especially close in on orbital periods like 150 days and shorter. So Proxima b is really one of these first highlights, very close to us, as close as you can get to the sun for finding one of these small planets. It continues the trend that we found with Kepler of these planets being very numerous, especially around the earliest, smallest types of stars.
Thank you. So you just mentioned that planets are everywhere, basically. And I just remind, you mentioned that in 1995, we didn't know any exoplanet. Most of us started our career as an astronomer without having the knowledge of any existing planet. And now, when I talk to the young generation, for them it's very obvious that planets are everywhere. And that's a game changer. And this game changer happened because of the Kepler mission, definitely. So now we know there is planet everywhere. We know there is a planet around Proxima Centauri. So my question is, Eduardo, could we image this planet? Could we finally see what this planet is really an Earth-like, a super Earth, or maybe something exotic that we don't even know about, such as a baby Neptune?
So thank you, Frank, for the question. And the answer, as most of the time in astronomy, is maybe. But before answering the question in more detail, I would like to give a little bit of background around Alpha Centauri, complementing what Natalie said. I grew up in Chile, and the latitude of the latitude of Alpha Centauri is -62. So when you are on the south, you see Alpha Centauri over the horizon, next to the Southern Cross, and those are the reference for kids when they go camping. If you get lost, the south is there, Alpha Centauri and the Southern Cross. Also, you use Alpha Centauri and the Southern Cross as a way to find Omega Centauri. So any amateur astronomer, any person that likes a little bit the sky in the south will tell you where Alpha Centauri is immediately. Moreover, Alpha Centauri is so bright that you see it naked eye even from Santiago, which is a super polluted city. You can see 3 stars. Okay, Alpha Centauri is there. So people come out from whatever, La Moneda or a university, and you see Alpha Centauri right there. So I mentioned this because this feeling, it's not possible from the north, from Europe or the US, and I think that for people in Australia, New Zealand, Chile, Argentina, for us, it's something that is right there. When I got my first amateur telescope, 4.5-inch Celestron, I was like 12 or something like that. And the first thing that I did, I resolved Alpha Centauri. And then you see the 2 stars, like it's super easy to resolve them with an amateur telescope. So Alpha Centauri has been on my mind for a long time. And I developed my career mostly on instrumentation and engineering. And then when I moved to NASA Ames, I had the fortune of work for Ras Velikov as an MPP postdoc. And then I discovered that Ras has a very, very similar interest on Alpha Centauri because of it's a unique system. It's so close. It's what you said before, is like within 10 light years, there are very few stars. And it turns out that Alpha Centauri is by far the closest by a factor of 3 in terms of sun-like stars. So then we start to work together on finding a solution to be able to image the habitable zone of Alpha Centauri, because it turns out that these 2 stars, Alpha Centauri, are sun-like stars, therefore the habitable zone is much farther out. And then it turns out that it's relatively easy to do that from space. Now, relatively. Now, the issue is Proxima Centauri is a brown dwarf. And as a brown dwarf, the habitable zone is much closer to a star. So we are talking around 50 milliarc seconds separation. At 50 milliarc seconds separation, you need a very big telescope to see that. And therefore, you have a situation where you have a very faint object that is like 1 million times fainter than the star. And you need to resolve it at 40 milliarc-second. As for just as a guidance, 1 arc-second is taking 1 degree, like the typical degree that we're used to, and divided by 3,600 times. That's 1 arc-second. Now you take that and you divide it by a factor of 20, and then you get to a 50 milliarc-second. So what we're talking is something really, really tiny, and the blur of the atmosphere is a lot more than that. Normally, the blur of the atmosphere on a decent side, on a telescope side, will be like around 1 arc-second. Now, when you go to Hawaii or the VLT, you're talking about 0.7 arc-second. So still, the blur of the atmosphere is a lot larger. Now, you can say, okay, let's go to space. If you go to space, the telescopes are too small. So when you have like Hubble or even James Webb, won't be able to resolve the distance between the star and the planet at the level of contrast that is required. So to answer your question after many detours, I can say that probably the best and maybe the only way to directly image and get photons from the planet is going to be using the European Extremely Large Telescope that they plan to build a high contrast imaging instrument called PCS, Planetary Camera, and that one probably will come online on 2025. The Extremely European Large Telescope will enter online probably on that date, but all these projects get delayed. So that's what I see on the horizon. The closest way to get reflected photons from the planet is a really, really difficult problem. Performing an astrometric measure on the planet, so basically see how much the planet is pulling the star, will create a signal of less than 1 microarc-second on the star. So you'll see a wobble of less than 1 microarc-second, which is, again, we don't have any instrument being able to detect that. So it's like a little bit like a paradox, so close but so far at the same time for direct imaging. So I think what Gilliam did is really fantastic. It's really unique science. And from my and Russ's perspective, I think our focus is Alpha Centauri, which is the other two system where we actually can do science, where we can have a meter telescope, we can resolve the habitable zone and try to see planets. How those two stars are related, we are not absolutely sure that they're gravitationally bounded, but we do think that it's a common system, and therefore it makes sense to go after Alpha Cent A and B.
Yeah, because the two systems, Alpha A and B, most likely form at the same time than Proxima, from the same cocoon, from the same material.
Yeah.
So if you have a planet like Earth around Proxima, you can assume you could have a planet like Earth around Alpha Centauri A or B. So that's a good sign for us. I mean, I'm extrapolating here, of course, but that's a good sign. What's very important, Guillaume, maybe you can tell us a little bit about this. What was the reaction in Europe, especially in the community of the ESO, and the people in charge of building the EELT and this instrument that will be capable of possibly detecting the light coming from Proxima Centauri B? Did you get any feedback from that? Did you get any thank you note or any I hope you're right because if you're wrong, you're gonna pay $1 billion for that? I hope you're right because if you're wrong, you're gonna pay $1 billion for that.
We talk with a lot of people. People is excited in general because they are scientists, but also they are people. And again, it's the nearest star, so you get excited with these things. But I agree with the diagnostics that Eduardo was doing. That, for example, to get direct imaging at this point, currently with the current things that we have, it's almost impossible. We are searching for transits, though, and that's something that still is work in progress. So maybe Natalie said we roll the dice and we get a 1/7 chances of getting the planet. That's true. Maybe we win the lottery and the planet is transiting, but that would be a lottery probability. But we are looking into it. So if we are lucky and the planet transits, within months we should be able to start to probe the atmosphere of this planet. That would be a real earthquake in the community. We'll see. It's a lottery thing. The probability is around 2%. However, the planet, we suspect, is probably smallish because of what we know from the statistics. So it's expect that the planet is close to the minimum mass. So we'll see what happens along those lines. I tend to have also a bit more constructive or more positive attitude. Of course, I'm excited, thinking that once you know that there is a planet or there is this object, you know the properties, you know the characteristics of the star. I hope people will get a bit more creative and motivated, and maybe a technological solution can be found even before the ELT. Maybe nothing happens as it was said. I also completely agree that the best chance we have to image exoplanets or Earth-like exoplanets is looking at alpha set A and B and hope for the best, that the planets are there. But I'm also a bit, I think when people get the news, they have the numbers, they know what they are looking for. Yeah, creative solutions can show up, and maybe we'll see what happens.
Okay. I would like to mention that, in fact, I've been already communicating with the group in charge of doing simulation of one of the EELT instruments, and they've been using the parameters of your planet already for the simulations. So they're going to soon publish some simulation of direct observation of Proxima Centauri b. I have a question for Tom, because we say we want to image a planet, but we didn't say why. So maybe Natalie or Tom, could you talk a bit about why it will be interesting to image this Proxima b? What kind of signal we expect to see, or what kind of image? We're not going to get an image. Just to clarify, an image for an astronomer is just a dot. Okay, that's an image. So before we get all excited, you're not going to see trees and stuff like that. You're just going to see a dot. Okay, so hopefully we're going to have an artistic picture taken by them, made by them. So please, Tom or Natalie, can you elaborate on
Why don't
this?
you say why, and I'll complement that with the pathways forward.
Yeah, I think one of we're right at the beginning of learning about planets around other stars. We've just started. In fact, we're living in the transitional stage. I think we're going to think of this time as a before and an after, and we're just after we know planets are everywhere. But we know so little about these planets that I think the next 30 years are just going to be an age of discovery. But we want to understand what these planets are like, what their characteristics. We know how far this planet is from its star. We don't even know its mass very accurately. We have an estimate of what its mass may be. But we want to know about an atmosphere. We want to know if this has an atmosphere, and if so, what's the atmosphere made of? And the reason we want to do this is because we know that atmospheres are required for life like ours, but also atmospheres can give clues about what is on the planet. We think our atmosphere was seeded, says clues for the early biology of Earth. We're doing a lot of work to try and understand what chemicals in the atmosphere tell us that life was likely appeared in that atmosphere, and what uniquely tells us about life, which are the biosignatures, as we say. So we want to go out and find these things, try and measure them, and try and say whether we think there's life here and life elsewhere. And that's the most exciting thing for me. It's using atmosphere, using chemicals to try and predict whether there might be life, or maybe was life on other worlds.
Mm-hmm. Yeah, so for the non-scientists in the audience, when light interacts with the atmosphere, the atmosphere leaves a fingerprint on the light that tells us about the temperature and pressure of the atmosphere, or the composition of the atmosphere, and we want to find life. That's the goalpost in the distance. So there's a 30-year roadmap for NASA to do this, and it involves direct imaging. And so in direct imaging, you've got the photons that are bouncing off the surface. So that's going to carry information not only about the atmosphere as it bounces off and goes back through the atmosphere, it's also going to carry information about the surface composition, different pigments, for example. Light reflects differently off of ocean than it does off of forests, for example. So if you can do this with direct imaging, you've got light bouncing off the full disk, and you're catching that and spreading it out into a spectrum. You receive a lot of photons. The other way to do this is with something called transmission spectroscopy. When a planet transits in front of the disk of the star, the light filters through the atmosphere on the limb, and again, it carries forward those fingerprints. But that's really tough because the planet itself is dimming 1 part per 10,000 the light of the star. The atmosphere scale height is only like 5 kilometers. So the area of that annulus is 1/200th of that. So it's really, really difficult. We think our best chance going forward for finding biosignatures is through the direct imaging reflected light off of the surface of the planet. We can do that from space. A 10 to 12 meter telescope is going to be able to image a planet, an Earth-sized planet, in the habitable zone of a G-type star like our sun. But for a planet orbiting M-type stars, which might be the most numerous out there, the habitable zone is really close to the star. You need exquisite resolution to be able to catch photons bouncing off of its surface. And that's going to require something like a 30-meter telescope from the ground. So you've kind of heard this now in a couple different forms. But the reason I think that this is really interesting is because we've got these two pathways kind of inching forward neck and neck. We've got these ELTs that are being constructed from the ground. There are, I think, 3 that are being constructed and should finish around the 2025 timeframe. And then we've also got this path forward for the space imagers like LUVOIR and HabEx that are currently undergoing concept design studies. And those funding is going to start to flow into those if indeed we find that those are the priorities. It's also somewhere around 2025. So it'll be interesting to see which one yields the life detection first. Ground-based discovery of a planet orbiting an M-type star, or a space-based discovery of a planet orbiting a G-type star like our sun. 2 very different scenarios.
Okay,
Frank, I have a question for Guillem.
go ahead.
Guillem, I'm wondering, what do you expect that can be done with Espresso? Espresso is an instrument that will enter at the VLT in service. It's a radial velocity instrument that's going to be 5 times more precise than HARPS. And probably you have been talking to the team, probably they're going to start operation next year. And do you think that you can get more information of the planet when that instrument is online?
Good question. At this point, we are sure that our precision is not limited by the instrument. As I mentioned before, and it happened any other times, the star itself is doing things that look like it's wobbling. It's like a boiling surface. So you see all these blobs of hot gas coming out and convection, and like in the sun that you see granulation, things like this. So if you naively use an instrument like Espresso or even HARPS and just point to nearby stars and try to get a lot of measurements without thinking a bit carefully, we won't do much more than what we are doing now. Don't quote me on that, but Espresso is a great machine and actually can do, the good thing about Espresso is that it's sitting also on a very large telescope, so we can do fainter objects. Things like this, but Espresso is also still a Doppler machine, can detect the motion of the star only. So, I mean, one of the things I want to do with Espresso is to get also measurements on Proxima, confirm it further with the 3rd instrument, and basically explore, for example, that there are possibly a couple more signals that look like could be from planets around Proxima itself. So things like this, even if you take Espresso and you have a planet like a couple Earth masses around Alpha Centauri or stars like this, Espresso is not going to help you much unless we really understand much better the physics. And I think the community would agree with that. So yes, this will be a great machine. We will no longer be limited by photon noise, but then a really top work starts where we basically need to understand the stars themselves at this level, and this is very tough. So I don't expect to have a quantitative leap in these kind of planets with Espresso until at least a few years after the machine starts to operate.
Very much. Also, I have a comment about what Natalie was saying. It's very interesting, the case of Alpha Centauri in that case, not only Proxima, but Alpha is so close that the habitable zone of those stars is around half an arc second from the star. So it's a very special case. And since those stars are brighter, the habitable zone is farther out, and we're able to see that habitable zone with a much smaller telescope, even half a meter telescope. That's the effort that Russ and I have been putting into trying to understand if we can fly a space telescope, a very small space telescope, 0.5 meter, that will be able to see those planets. Now, that telescope will be able only to access those two stars, and that's it, because everything else is farther out, and therefore has to be like a really specialized telescope. And as Natalie was saying, there is this race, and instruments are getting more and more complex, more and more expensive as well. Therefore, a specialization into a particular system makes a little bit of sense as things get more complicated. And I think that that's a trait that we're studying, and those are the alternatives that we need to decide which are the best strategy to go forward.
Since we are talking about our instruments, and you mentioned a competition between space and the ground, I should mention
Say the word competition. I said they're both
Friendly-
inching forward.
friendly
I think
competition.
we need to do both. They're complementary. They don't measure the same things.
we also have a group that I'm working with. We also have a project of searching for an Earth-like exoplanet around Alpha Centauri, using this time a 8-meter class telescopes. And we are confident that it will be possible to observe, because of the large separation between an Earth-like exoplanet and the star, such a planet with only an 8-meter class telescope. So it's
Wait,
gonna
8 meter from the ground?
from the ground, yes, using the new adaptive
But
optic
can you
systems.
get down to the contrast that you need?
Thermal imaging,
10
that's the
microns.
trick,
Yeah,
yes.
yeah, yeah.
Okay, we're gonna open the floor for questions. Is that okay with you? So, who has the microphones? I saw someone with a microphone here. Okay, yes, Lee, can you take care of that, please? Thank you. I'm taking care of this side to help you, if you want.
Oh, hello. So I was wondering what sort of atmospheric circulation model you are assuming, since the planet may be tidally locked, what sort of atmospheric circulation you are assuming to claim that it's habitable? And another question is, do you think that high energy particles, because it's so close in, could pick off the atmosphere over time?
So that's for Guillem mostly, right?
I don't know if it's habitable or not. What we know that it has characteristics that potentially can lead to a habitable atmosphere. We actually participated in some of the follow-up studies to calculate these possible atmospheres that we can have around this planet today. And basically, the basic message is that the parameter space is too large, and we don't know how these planets form. We don't know if they are water-rich or if they are dry from the beginning. What we know is that in the range of things that we could expect from our very biased understanding of the situation, there are a number of solutions. You leave the planet, you put an atmospheric model, you leave it tidally locked because it's probably locked. It's true that it's looking, one side of the planet is probably looking at the sky all the time, but then a global circulation atmosphere model typically by itself always generates currents that keep all the planet warm. So you don't have a cold trap where the planet, all the water goes into one side of the planet and gets frozen. This is what the simulations are telling us. There are also solutions that lead to Venus-like environments or even Mars-like, where all the oxygen is either going into weird chemistry, like Venus, or it oxidizes the surface and it's absorbed by the mantle. Things like this can happen. But one of the things that can happen also, one of the solutions is you end up with a very deep ocean, for example, water wall. If you start with a lot of water, like 10% of the planet's composition in water, you will never lose so much water, even with very strong radiation. So the thing is that the options have all possibilities. Is what I'm saying. This is a different world. We have to figure out how it is. But it's a real, there is a region of parameter space that allows to have a relatively Earth-like conditions, given a lot of caveats. But yeah, we'll see. I mean, it doesn't need to be Earth-like. For example, to be life there, it just need to have some abundant water, to have some complex chemistry, for example. And so that's what we need to figure out with observational constraints.
Someone want to add something about
I'll
this?
just say the important phrase there, I think that Guillaume touched there right at the end, was observational constraints. From the panelists and other scientists, I think it's short-term, very difficult to get observational constraints. So a lot of things you hear in the press right now and people's models is all great, but they're theories at this point. And this is the way science works. I'm more of an observer, so I can make fun of the theorists, but they have good ideas, and they're exploring the parameter space. But you can't make any definitive claims about the habitability of this planet without observations. We can't do those now, but that's what drives us in this field is observational tests so that we can answer these questions. We just don't have the answers right now.
Well, I think that it used to be that tidal locking meant game over, no possibility of being habitable, and I think that's changed. The utility of the theoretical models is to explore the realm of the possible. And with climate models, circulation models, and the like, I think now we're in a position to be able to say that it is within the realm of the possible, that the atmospheric circulation will keep temperate regions temperate, and that you won't evaporate. On the star-facing side, you're going to create lots of clouds because you're going to evaporate all of the water, maybe even dissociate hydrogen and oxygen and evaporate off the hydrogen. You're left with only oxygen. Meanwhile, you've got this huge thermal gradient. You start driving material to the backside where it all condenses out and freezes out and gets locked there. So now you don't have any liquid water left, as time proceeds. But that picture's changing. I think that is certainly one potential scenario. But the circulation models are saying that no, it can equilibrate and create temperate zones that are stable over time. It's helpful to know that it's within the realm of the possible.
Okay, we have a question. Okay, here.
Yeah, hi. Thank you all for coming. Great talk. I just wanted to know, I heard some chatter going around that potentially the James Webb Space Telescope may be able to do some observation of this planet. And then a follow-up to that, I was wondering, I've heard of a group that is trying to do a space coronagraph, and I'm wondering if a space-bound coronagraph would have any potential of imaging it, or would the separation be just too small and the coronagraph would get in the way? Thanks.
Let's start with the...
Maybe just to comment on JWST, and then Eduardo can comment on the imaging. Your question was multifold, and I'm not sure I got all of them. But JWST will make an impact if this object turns out to be transiting. I talked about the transit geometry and that thin layer of atmosphere. Even given the difficulties with JWST's aperture and the fact that this object is so close, and yet it's not so bright that the JWST instruments will saturate, which is key, it would be able to get a transmission spectra. But again, as Guillaume already mentioned, that probability is 1.5%. It's pretty tiny that it is in that right geometry. JWST will not have the inner working angle to be able to resolve this planet. Its aperture is not large enough.
Guillaume, I heard there is a group who wanted to analyze all the MOST data taken to see if there was any signal of transit. Have you heard news from this data analysis?
It's work in progress. I cannot comment much on that, but we are trying also with other ways, ground-based and other options. Yes.
Okay. You want to answer to the second part of the question?
So, regarding the coronagraph, even from space, it's very difficult to get to 50 milliarc seconds separation because the planet is really close, and you will need a really big telescope, even bigger than James Webb, to be able to do this. So it is very unlikely that we have a space telescope that will be able to do that. HAVEX and LUVOIR, maybe. These are long-term concepts that NASA is discussing as flagship missions for 2030, but we're talking 20 more years, so nothing in the short horizon. There is another mission called WView First that's supposed to launch in 2025. It's a 2.5-meter telescope similar to Hubble, and that will have a coronagraph, but still the performance of the coronagraph won't be good enough to be able to see a planet around Proxima Centauri.
The aperture just won't be big enough.
Yeah.
Okay, this question is for Guillaume. First, congratulations on your discovery. But you mentioned in passing that there might be future discoveries around Proxima of planets further out. and one of your slides showed that the habitable zone is up to a 30-day orbital period, and we got, I think, as I recall, an 11.2 day on this one. So my question is, are there currently follow-up studies to try and detect further planets around Proxima Centauri? And if so, have you been able to rule out any other planets in the habitable zone, or could there potentially be further planets in the habitable zone around that star?
Okay, several questions here. First, the data already shows signals of another planet at longer periods, but we don't know if it's rotation or activity of the star. That's the one quick answer. Beyond that, there's no evidence of anything else in the data as we have it now. However, and this is pure speculation, the people also running planet formation models tells us that when you form a planet about this size or telluric or even larger, they usually tend to come in packs of planets, smaller ones. So it is possible that this is the largest one of a number of small is a shepherd of a number of planets that came migrating through the disk. But this is pure speculation at this point. So that is possible, that there are more planets. The data is not yet good enough to see them, except this one that it's an outer one, and but that's another story. We'll see what happens with that. And yes, we are following up, at least on this second signal. Let's see what happens.
Okay, thank you.
Hi. I wonder what the change of subject, I guess, but I wonder what the panel thinks about the Russian radio signal and what questions you have about it already.
Well, I wrote a blog post about that, so I recommend you check it out. That may be the fastest answer. And there is also an article on our SETI website. Let's keep the topic on Proxima Centauri B.
I mean, the short answer is that nobody else has seen it.
Yeah.
Guillem, I was wondering if you could speculate about what do you think is happening around day 80 of your data? It looks like, based on the error bars, I'm just curious, what do you think is going on there?
What do you mean, at the end of our data?
Day 80 of your data.
Yes, something happened there. It's a combination of bad weather, because the El Nino started to hit, apparently. So the data is not as good quality as before. Also, we suspect that Proxima has these active regions, and when they show up, the radial velocities get way worse than usual. So you have this rotation of 83 days, and if there is this active region, when you see it, the measurements are not as clean as they are. This is probably one of the reasons also why it was difficult to spot the signal so clearly before. So yes, something happened there, but statistically speaking, these points are consistent with white noise, basically. We'll see. We would really need a longer campaign to study it better.
Guillem, you just alluded to this earlier in your reference to the planetary models. What, if anything, can we say or speculate about the age of the planet, especially relative to, both to Earth as well as to other stars that we find, to other planets that we find?
Yeah, I mean, basically, there's an age estimate coming from Alpha Centauri A and B, because for M dwarfs it's difficult. But if you believe that the three stars are bound together and come from the same origin, the system has around 4.85 billion years. I mean, there are error bars, but it's sun-like in that term. It's metal-rich compared to the sun, so it's about 1.6 solar metallicity, something like this. So yeah, that's what I can tell you from inferences from the system, basically from Alpha Cent A and B that are much easier to measure ages and calibrate them.
We have one more question.
Looking at the signal on this last graph, there's a blue sinusoid, which is the assumed radial velocity, but I noticed that it's slanting down. What is that long-term effect?
That's what I'm talking about. There is this additional signal, either coming from a planet or from stellar rotation. But it has to be quasi-periodic at least, because we know from long-term baseline that this trend doesn't hold over time. So it has to be wobbling around. So it's either a signal of a planet, additional planet, or rotation. We are sure, or stellar activity. It's an additional, what I call a signal. To transform that into a planet candidate, then there's a lot of work, but we need an optimized campaign to explore that.
Okay. I'm very sorry to be the one, but we have to stop this conversation. Thank you very much, Guillaume. Thanks a lot, our panel. And I would like to say that the next time we're going to have a panel like this will be when we have an image of Earth-like exoplanet around Alpha Centauri. Okay? It's a deal? And the same people, please. Okay? Let's say 5 years, 10 years. All right. Thank you very much. Thanks a lot.